brightness, most stars lie along what we call the main sequence. So most stars lie along here. Here's the sun. So this is the intrinsic brightness, and the sun equals 1 on this plot. So here's the sun. It's 5,000 Kelvin at the surface, approximately. And we label it the luminosity of 1. So these stars on the main sequence are bright and blue. So you can see that they're blue. And these stars on the main sequence are cool and red, and low and faint and red. So most stars in the sky lie along the main sequence. And the main sequence, someone mentioned it earlier. This is where stars spend all of their lives burning hydrogen to helium. They spend 90% of their lives on the main sequence. And so this just means these stars up here are very massive, and they are hot and very luminous. And these stars down here are lower mass than the sun and cool and faint.
这张图大家在地科的课本里面可能学过，我如果没有学过的，我给你解释一下。这张图是纵轴是画恒星的光度，它实际发光的能力；横轴呢是画恒星的表面的温度。不过因为习惯上，天文学家把比较高的温度呢画在左边，所以左边是高温，右边是低温。高温的发光体发出来是比较蓝色的光线。 低温的发光体发的比较黄色、红色的光线，就是这张图的意思。那你如果把人的身高跟体重去做图的话，身高跟体重常常会有一个正向的关系，对吧？高的人通常比较重一点，当然会有例外，不过主要都是这样子。那你如果把天上的恒星也做这样子的统计的话呢，你就会发现从左上到右下有一条叫 main sequence， 刚刚有同学讲叫主序。 因为恒星花90%的时间在这个位置上，这什么位置呢？就是越高温的恒星表面很热，它发光能力就会很强。那右下角呢，就是很暗，那表面温度就比较低。这是一个所谓正常的恒星，而所谓正常的恒星，就是在它的内部核心的当中，正在把氢转换成氦，就刚才讲的那个过程。 这种恒星，我们把它定义成叫做主序星。
So 90% of their life they live on the main sequence, and these massive stars up here, when they finish hydrogen burning, when they start burning helium, they move across, and instead of being blue, they become red. Does anyone know which constellation Betelgeuse is in? Does anyone know the star Betelgeuse?
Betelgeuse 在哪一个星座 ？Betelgeuse 就是参宿四。参宿四在哪一个星座？啊？猎户 Orion.
Orion, yes. It's the bright red star in Orion. So Betelgeuse is here. So it used to be a main sequence star, a hot blue main sequence star. But now it's near the end of its life. We don't know how close. It might explode as a supernova next week, or in 100,000 years. But it's over here in the HR diagram. It's finished burning hydrogen, almost certainly, in its core, and it's nearing the end of its life. So stars get cool, they move over here, and we think they have a structure something like this towards the end of their life. And this is what happens to all massive stars. They become redder and cooler, they expand, but their cores become made of the heavy chemical elements and eventually iron.
刚刚举了一个例子，就是 Betelgeuse，Betelgeuse 就是参宿四啊，就现在冬天可以看得到猎户座。那颗星已经离开主序了，它已经中间不再靠氢来进行核子反应，它已经到红的那一边去了。可是它还很亮，它不是正常的星球，对吧？它很红，很低温。 每一个低温表面只能一点点的辐射能力，为什么可以这么亮？表面积很大，体积很大，所以它这些叫红的超巨星啊。这些星球它已经不在主序了，那一般相信它中间的那个核心的结构呢，很像洋葱一样，因为它原来在主序的时候进行了一系列的核子反应嘛，从 氢啊、氦啊、氧啊、碳啊、氧啊这样一路下来，最后到铁。所以相信它的最中间 iron 有一个铁，外面包了一层气，在外面包了一层氧啊等等等等。这是一个例子，就是一个质量是太阳25倍的一个恒星，它刚刚离开主序，还没死亡的时候，它的结构应该是像洋葱这样一层一层的，都是重金属。
So one very important thing here is that this is what we observe. So we can measure temperature, the surface temperature. We can measure how bright the stars are. We actually see stars here. So we see Spica here. We see Betelgeuse here, Rigel, Vega, the Sun. This is what we observe. And this is our theoretical model. This is what we think is going on in the center of the star. So we use this, observations, experiment, to test our theories in the core of the stars. That's a very important difference between these two figures. This is observational, this is theory.
左边是真正观察到的，右边是理论，是猜的猜它的结构，不知道真正星球结构，量不到。
So here is a comparison of the size of some of the biggest stars in our galaxy. So this is Betelgeuse, this is Antares. The Sun is this size, the size of my laser pointer. That's the radius of the Sun. Rigel, which is a blue supergiant, is this size. So these are huge stars. They are about 10 times more massive than the Sun, but they can be 1,000 times bigger in radius. These are called red supergiants.
这是照比例画的体积用画的。那上面左边就是刚才的参宿4，右边是 Antares， 是星宿2，是天蝎座的那个主星，也是一个红的超巨星，红超非常大的巨星。像他刚刚讲的那个镭射光点啊，大概就是我们的太阳，这些星球大的不得了。
So right in the cores of these stars, when they reach the end of their life, the iron core is 100 times smaller than the size of my laser pointer.
这个阶段的核心，大家看到这个大的这个红色是它的气体，是它原来的大气层。真正的核心，刚刚讲像洋葱一层一层的，是比刚才那个镭射的这个镭射笔的那个光点啊还小100倍。核心是非常小。
So in the iron core, it's this size, 100 times smaller, but it's got a mass of 1.4 times the size of the Earth, the Sun. So imagine the mass of the Sun, 1.4 times the mass of the Sun, squeezed into the radius of the Earth.
大小虽然很小，就是刚刚讲光点就大小就像地球这么大了啊，但是包含的物质呢的量啊和质量呢，有太阳的大概1.4倍，所以你把一个太阳现在这么大，是我们地球1000万倍的压到像地球这么大，就是这个铁的核心的密度，它的那些性质就是这样。
So once we reach iron, once the core is made of iron, that cannot produce any more nuclear energy. It cannot burn to the heavier elements and produce energy. There's just no way of doing that through basic nuclear physics. You cannot produce any more energy by burning iron to heavy elements. So when it's made of iron, the core runs out of energy. And what do you think will happen to the core when it runs out of energy? It's 1.4 times the mass of the Sun, squeezed into the size of the Earth with no energy to hold it up. No nuclear energy. What will happen to the core? Not the whole star, just the core. Did someone say explode? Before it explodes, what will happen?
这么密的东西，它会说会怎么样？一个像太阳这么多塞在一个像地球这样的大小，已经是铁了，没有办法再靠缩下去、温度上升产生核融合。刚刚讲核融合制造铁，对吧？所以没有办法再进行核反应了。这个核会怎么样？这个 这个星球的核心会怎么样？刚刚的问题。刚刚有人说会爆炸，或者说在爆炸之前会怎么样？
It will be hot, but still not hot enough to hold itself up. What will happen?
It will collapse.
It will collapse, exactly. So what happens is that the iron core collapses from the size of the Earth to 10 kilometers in a fraction of a second.
会发生什么样的事情？如果像地球这样，已经现在地球这么大了嘛，刚刚回答说它会因为万有引力太强，会把它让它塌缩下去。 说到只有10公里，就台中市这么大，把地球压成只有像台中这么大，会怎么样？可以动。Becomes a black hole.
Ah, maybe. First, it probably becomes a neutron star. So the core collapses. What we think happens in a supernova is that you have an iron core, only the core collapses from the size of the Earth to 10 kilometers. We think we get a huge burst of neutrinos. Neutrinos are fundamental particles that have no charge, extremely light, and these are produced when the core collapses. Let me take you on a little bit. So, supernova energy, if you've got a star which is 20 times the mass of the Sun, let's just think about its core. This is the size of the Earth, 10 to the 3 kilometers, and it's 1.5 times the mass of the Sun. This collapses to a neutron star, 10 kilometers. So what type of energy does that release? If something drops under gravity, what type of energy does it release?
原来是一个20倍太阳的恒星，超级大，中间的核心就很小，把它放大出来，中间大概只有1.5倍的太阳质量。比如说这个粒子，那只有地球般大小，然后后来又缩下去，缩到全部都是原子核了，对吧？就是刚刚讲的中子星，缩到只有10公里大小。一个东西从很大缩到很小，也就是因为万有引力 而缩小会释放什么能量？这个问题。
So if I have something and I drop it,
对，
what type of energy?
释放了什么能量 ？Potential.
Potential. Gravitational potential energy. So imagine 1.4 times the mass of the Sun collapsing in a fraction of a second. That releases energy. Does anyone know remember the equation for gravitational potential energy? I won't ask it. Does anyone recognize it? Have you used equations for gravitational potential energy in physics class?
你们的物理课有没有学到万有引力位能的公式啊？有啊。Oh, yes.
Yeah. Okay. So, gravitational potential energy of the core is this. It's G times the mass of the core divided by the radius of the core. This is the core before collapse. So that's it before. Gravitational potential energy is large and negative. And if you subtract the gravitational potential energy of the neutron star, this number is much bigger than this. So the gravitational potential energy of the neutron star, if you work it out, it's 10 to the 46 joules. That's the amount of energy released in a fraction of a second. And this 10 to the 46 joules is what powers a supernova explosion. The collapse of the core, release of gravitational potential energy, and that gives us 10 to the 46 joules. Now, to think of how, that is a really big number. To think how big it is, if you think of E equals mc squared, this is the equivalent of 50,000 Earths being completely annihilated in a nuclear explosion. That's the equivalent energy which is released when the core collapses. This is a huge amount of energy when this collapses from 1,000 kilometers to 10 kilometers.
Gravitation 万有引力啊，重力 gravitational 万有引力的 collapse 这个字就是他说，他说跟收缩有什么不一样？收缩是一个广义的词，他说就是好像一个楼啊，突然间没有支撑了，滑下去，这叫他说。刚才讲的一个核，它没有万有引力了，没有东西挡它，没有阻挡力，所以它的缩下去是他说，非常快，不到1秒的时间，就刚才讲的这个从大到小就缩下去了。那要释放多少能量呢？刚刚大家讲的是万有引力了。万有引力跟刚才讲的原子核，我们讲核反应，好像核反应很有效率，对不对？可是呢，万有引力呢，它所占的空间很大，所以它总能量还是很多。这边做一个很简单的计算，你把原来的万有引力位能、重力位能跟缩到10公里左右、1.5个太阳质量的重力位能来比，这你们都可以算，很简单就可以算。算完以后你就发现，释放出来的能量是10的46次方焦耳，大的不得了，能量很多，这个空间大，对吧？这个释放出来的能量在不到1秒钟之内，这个能量就要释放出来，难怪超新星会这么亮啊！不过这边做了一个比喻，这能量到底有多大呢？就是如果用1等于 mc 平方来换，我们本来说 m 只要一点点，因为乘上了 c 平方很大的数字，能量就可以很多。那这个能量多到什么地步呢？10的46方带回去，那个 m 呢，相当于5万个地球，把5万个地球全部转换成能量，在1秒钟之内就要释放出来，这么多的能量。
So this is the energy released. What we think is that when this collapses and we release 10 to the 46 joules, most of it actually is released in these neutrinos. The star gets a neutron star created. So we think a neutron star is created, which is like a giant nucleus, the density of atomic nucleus. Neutrinos are emitted, and these help to create an explosion in the star. This is probably the most uncertain part of supernova physics, and many groups in the world are trying to simulate this on computer simulations to see if they can create theoretical explosions that actually work. And they're generally driven by these fundamental particles called neutrinos, and there's very complex physics used to try and explode the star with this burst of neutrinos.
Neutrinos， 看它的英文这个有这个 new 啊，所以它是中性的。trino 就很小，所以 neutrino 中文台湾翻成微中子。微中子它不带电，中嘛啊。那微就是它几乎没有能量，可能完全没有，或者很小很小，到目前还没有很确定。这种微中子呢？很多，然后不太跟东西反应。在超新星爆发的时候呢，微中子扮演了很重要的角色。原因是这样，我们平常在上课的时候，我们说，原来是质子、电子，那你把电子要压到原子核里面去，因为压得很紧。原子核里面是什么？是中子跟质子嘛，对不对？那你把电子压进去了以后，电子就会跟质子结合，变成中子。所以整个东西就变中子，所以才叫中子星。可是这个过程要释放微中子，而且释放很多微中子。这些微中子呢，是超新星爆发扮演很重要的角色，因为它带走能量，等等。但是这一部分的物理还不是很清楚。你想想看，这么多能量，完全超乎人类的这个习惯的这个尺度，要在这么短的时间释放出来，这一部分的天文物理的模型呢，还不是很完善。到底怎么样发生？但我们知道一定有有很多的 neutrinos 要被释放出来。
So we think the neutrinos drive an explosion in the center of the star, which rips through the star at 40,000 kilometers per second. And when it hits the surface, that's when we see the supernova. The surface of the star gets very hot, very bright, and the star starts to expand, and that's when we see the supernova. Now this is a theoretical idea. The idea of core collapse is theory, but we can test this, and we have tested this with supernovae. So in 1987, we saw a supernova in the Large Magellanic Cloud. Before explosion, there's a massive star there. The star was 17 times the mass of, this means mass of the sun, 17 times the mass of the sun. We know the star has disappeared, and neutrinos were detected in 2 experiments, one in Japan and one in the US. And the Nobel Prize was given for the detection of these neutrinos from this supernova. There were only 13 neutrinos detected in the 2 experiments. But this shows us that a supernova occurred, a massive star disappeared, and we detected neutrinos. So this is good evidence that that model is correct.
整个这个塌缩的过程啊，刚刚讲的核心塌缩，核心没有支撑力量，它就缩下去。可是缩下去以后就变成中子型，中子很坚固，对不对？压不下去，压不下去怎么办？反弹回来嘛，所以就把外面的东西炸掉，就看到了爆发。Supernova 1987A， 刚才有讲我忘了解释，这个那一年的第一个就用大写的 A， 然后第二个就是 B， 一直到 Z 大写的。第27个呢就用小写的 AA、AB、AC 这样。你刚刚前面看到 BU 啊什么，就表示说现在发现超新星的这个成功率很高。当时还没有很高，是在南半球的天空，台湾看不到。在爆发之前，我们看到一颗星，这个地方爆发之前是有照片、是有资料的。爆发之前一个恒星，然后呢，爆发之后，当时是1987年的2月14号，情人节当天，爆发的光到了地球，地球人发现这个超新星。那讲这个超新星现在研究很透彻，因为我们这一辈子新的仪器去研究它，发现它的前身。它的 progenitor 是一个14个太阳质量的恒星，然后呢，爆发完这个星就不见了。我们的理论是对的，超新星爆发是恒星死亡这一件事情，如果真的是新星刚刚诞生的，应该要出现一个恒星嘛，对不对？就是超新星是回光返照了啊。然后呢，另外一个也是实验，也是天文物理很大的胜利，就是 neutrino。我们原来那套理论说缩下去，然后中间产生中子，一大堆的中子，会发射一大堆的微中子，微中子跑到地球，被地球上面的2个实验，一个在2个仪器，一个在日本，一个在美国，侦测到了微中子，只有17个事件就是微中子抵达了。但因为这样子，那一批人也得了诺贝尔奖，因为他验证了说，我们原来理论上认为恒星死亡产生超新星的这件事情，实际上我们在有生之年真正看到了这样的事情。
This is actually a plot of the neutrinos. This is the time, and this is the number of neutrinos detected on Earth. And you can see over 12 seconds, there were in the Kamiokande experiment in Japan, there were 11 neutrinos, 11 or 12 neutrinos detected in 12 seconds. A small burst of neutrinos, but enough to say that it came from this star. So this is our observational data to test our model. So what I do, I'll talk to you now about the research that I do on supernovae, because this is theory. This is what we think happens. What we want to do is take observations with telescopes and try and test the theory. Does anyone know what this is?
Space telescope.
The Hubble Space Telescope, yes, exactly. So this is a telescope that I use frequently for my research and have used for many years. Try and test what we think happens at the very end of the life of massive stars before they produce supernovae. Here's a picture of what's called the Hubble Ultra Deep Field. The Hubble Space Telescope looked at this field for about 10 days to 2 weeks. It stared at one patch of sky. It took images at different wavelengths. And this is the deepest image of the sky that's ever been taken. If you look at this, most objects here are galaxies. So you can see that these are extended objects. Some are spiral galaxies. There's a spiral galaxy. Some are elliptical galaxies, like this. orange, red, elliptical galaxies. There are very few stars in the field. That's a star. That's a star. But most of the rest of the objects in this field are galaxies. Hubble looks at very faint things. If they're very faint, if these galaxies are very faint, what do you think it tells you about the distance? They're very far away. So these galaxies are very far away. Some of them are, so the universe is about 13 billion years old. Some of these galaxies were formed when the universe was around 1 billion years old. These are the most distant galaxies that we can see. So this shows you the power of the Hubble Space Telescope. It can see very distant galaxies. It can look at these galaxies with fantastic resolution because it's above the atmosphere of the Earth. So it gives extremely good image quality. It gives very fine resolution and almost perfect images from space. Hubble also looks at nearby galaxies. These are 3 pictures that I've taken with the Hubble Space Telescope. They are nearby galaxies like the Milky Way. They're full of massive stars. Now, these are the galaxies that professional astronomers and amateur astronomers search for supernovae in. So people can find supernovae in these galaxies, and Hubble has also taken pictures of these galaxies. So if we find a supernova in this galaxy, we could go back and see if we can identify the star that exploded. The resolution of Hubble and the power of Hubble is good enough that you can actually see individual stars. I'll show you some pictures to show you we can see individual stars in these galaxies. Let me come back to this number, but I'll show you this first. This is a zoom in from the ground, a ground-based image, right into this galaxy. And then finally, this square is the Hubble image. This is an image from Hubble in the same galaxy. And we're looking in and zooming in on stars in this galaxy. So every star in this image is a star in that distant galaxy. That's a galaxy called M81. Would you like to see it again? So these are stars in our own galaxy. This is the M81 galaxy, and now we zoom in with Hubble to look. And this is actually a supernova that exploded many years ago. But all of these objects, all of these stars are stars in that galaxy. So Hubble can see stars in distant galaxies. Now imagine that one of these exploded as a supernova. We could go back and actually see which star exploded. Hubble has been observing since it was launched in 1990. It had a problem with its mirror, and then was fixed in 1993. So it's been observing for nearly 20 years with good image quality, and it's observed most of the galaxies in the sky, close to the Milky Way. So now that it has observed most of those galaxies, we can observe we can check for supernovae in hundreds of these galaxies. And when we find them, we go back and see which star exploded. And that's what we use to test our models of supernovae.
SMART 教授他们的研究呢，就是刚才讲的一些超新星的理论，还有观测的手段，希望收集到够多超新星的性质来验证这些理论。那其中一个工具呢，就是当然就是望远镜，一个很重要的工具就是哈勃太空望远镜。哈勃太空望远镜1990年放出去，登升空，发现光学有点问题了，93年帮他配了一副眼镜，所以他就看得比较清楚。就修正了以后呢，到现在已经超过20年，哈勃已经很老了，退休了。那刚才有看到几张投影片，有一张是哈勃的 Ultra Deep Field， 非常非常深级，就是即使在太空，太空有什么好处？没有大气的干扰就比较很清楚，而且可以看别的波段，在地球大气之内看不到。即使在太空，它还是有日夜因为它绕着地球轨道，还是会有太阳还是有白天，对吧？所以他也不能一直看一个地方，一直看，所以他就看， 把影像记录起来，然后可以看的时候继续看。Ultra Deep Field 呢，就是针对一个很小一块天区一直看，收集了将近2个礼拜左右的时间曝光时间。那看很暗的东西，很暗的东西，它光刚刚表示它多半很远，很远呢，它光线要花很久的时间才来，就表示它是很老以前的东西，是很年轻时候的宇宙。你刚才那张照片里面有好多星系，都是叫宇宙本身只有10亿年左右的时候，宇宙本身宇宙现在是140亿年的年纪了，那时候只有10亿年的情形。那这个呢，就是说，因为哈勃的影像很清楚。